So why we are doing that part? It is clear that we want to analyze our system, which could be a mechanical system, which could be a thermal system, whatever the system is. Because each system can be represented by an equivalent and electrical analogous system. We have studied about electrical analogous. If not, then I will explain you. Because taking was complicated. And then I will explain you about the electrical analogous of the mechanical system to electrical system. Suppose your mass is there, spring and damper, which is going to represent your suspension system. Okay. So that can be represented by an equivalent electrical circuit. It could be R, L, and C. So what the problem is there? The then problem is that you have with the sizing of your, let's say, electricity mass system is there, and then you have sized it with spring constant, damping coefficient, okay, mass and everything is there from pole to the actuator. You want to analyze it from simulation because the differential equation is becoming complicated because you have multiple dampers, multiple springs are there, maybe different mass is being connected here. So it will be very difficult for you. So what is good? That you get an equivalent electrical analog system, okay, analogous system for your that mechanical system, and then obtain the block element wise block diagram representation. With each system, each component will be represented by a transfer function. Transfer function, a block, small block, and then put it arrange it into your simulation tool, which can be a MATLAB, which can be Scilab, which can be any other thing. So this is what the equation is. Just for example, let me explain you. Suppose that you are having, because you are having a mass here. Mass is here. It is connected. You see a spring, and let's say a damper is connected here. This is mass, this is spring constant K, and this is B, and let us consider that some force acts over it, this one, okay, some force is there, Ft acts over it, and because of that, what happens, some displacement X is occurring. So how to analyze such type of system? It will be very difficult for you. You can write down the equation. So you know like how we write the equation. I think you would have studied already. This is X, let's say, that here a mass is connected, mass element is connected, then a spring element is there, okay, then you are having a damper connected at this end point, okay. This is B, this is K, this is M, this is X, and let this force, what it is acting over it is, let's say this is represented by this force, which is your Ft, okay. So you'd be knowing that this you can write down the differential equation of this equation system is mx double dot, where x double dot is double derivative of x. This is d2x over dt square, which is your acceleration. Okay. Then bx dot plus kx equal to ft. This is what we see. This is your differential equation, where x is what? It is a displacement. Okay. X dot is the speed. Okay. X dot is what? Dx over dt, which is the speed. Then x double dot is the acceleration, d2x over dt square, that is acceleration. This is what. So you see that we are, I hope you know this one. This is taught to you already. Okay, now we can represent this particular system with an equivalent electrical system. Okay. So let's say that this and that equivalent representation can be what? It could be two types of different representation. Means you can represent this system by an equivalent R, L and C circuit. This is R, this is L and then this C. At the input, let's say that some voltage is given. So this is U is the input. Okay. This is there, and the current which is going to flow in the circuit is, let's say, I. And also you can represent the same system by parallel arrangement. Like you see that R, this is L and this one is C. R, L and C. This in this way, and then this will be excited by a current source. This will be excited by a current source I. And this will be R, L and C. This is excited by a voltage source. Let me write in place of U, we write a back EMF source E. Okay. So you can represent your system in these two ways. So what at present we are seeing is an analog electrical equivalent system, analogous equivalent. And we are talking about analogous system. Okay, analogous system. So this is called force voltage analogy. Okay, force voltage analogy, and this is called force current analogy. Okay, force current analogy. The two way you can represent your system. This is clear to you? Okay. So is it possible that you can write down the equation for this? So let me make it another one. So we have one equation, you have seen that we have a mechanical system in which we are going to represent it by x dot plus kx is equal to force, where x, this is Ft. This is mechanical system 1. And then we had considered that a equivalent electrical system, okay, like this. This is R, L and C, and here we have given an input, means a force input is there, EP, okay, and this is C, and the current which is going to flow in the circuit is I. This is clear? So can you write down the KVL? Let's we together write KVL. So it is what? Rise in potential. So rise in potential is what? Positive back EMF. Then we are moving in the direction of current. So that is minus I into R. Then we have an inductor element, that is drop in potential again, minus L di by dt. And then this is again, okay, drop in potential. So it is minus 1 by C integral I dt. I hope there is no doubt over this one. Okay, because we have studied it. Okay. So one thing is that we have to get some differential equation like this. So one relationship we are having. What is that? I is equal to dq over dt. So can we substitute this I wherever is required? Wherever it is required. And similarly we can write it like q, we can also write is as integral I dt is equal to q. Of course you will be writing from minus infinity to t. Minus infinity to t. This is you have to write. Okay. So you see that just substitute this equation into this one. So what we are getting, can you see that it is back EMF E, then R dq over dt, then minus L d2q over dt square, okay, d2q over dt square, then this is what? Minus q by c equal to 0. Means I think by this time you would have got like what actually I am willing to do. Okay. Now so we are rearranging this equation as L d2q over dt square plus R dq over dt, then plus 1 by c q equal to this back EMF. So do you find some similarity between the two systems, two equations? Because what we do that when we say that we are modeling the system, then you can make what? Like write it by writing the differential equations. Okay. So differential equation is nothing but what? We have applied the laws by which that system is being governed, and then we apply there, like here we have applied laws of motion, and so we got the first equation. Here we applied the Kirchhoff's law, and we got the second equation for the vector. So what law is getting governed, being governed, you take the help of that and write on the equation of dynamics. Okay. So you see that this is your second equation. So if you check, compare these two equations together. So can I write here m? Here also I am writing just to avoid any confusion with you, is that b dx over dt plus k x is equal to ft. Now please compare the two equations. So if you compare here, you will find that mass in a mechanical system is equivalent to inductance. Clear? Similarly, a damper in mechanical system is equivalent to resistance in equivalent electrical system. Okay. Similarly, a spring constant K is equivalent to the capacitance, okay, of the equivalent electrical circuit. This is clear? No? So, can we say here that we are having, so can we say that if we are having a mass damper, let me draw a mass damper system once again. Okay, this is m, this is k, this is b, and we have written what? These equations. So these two are equivalent to each other, what we are saying, analogous to each other, and this is what? Force voltage analogy. Okay, so here can we say that this system can be drawn equivalently to an equivalent RLC circuit. This is basically like a suspension system. You remember that? You have already studied in mechanical. So can we say that this spring constant K is equivalent to what? You see, capacitance. Okay. So wherever you see K in your system, we put just 1 by C. Clear? Or wherever you see C in your system, electrical system, you can replace it by 1 by K to represent your mechanical system. Okay? Then here m is equivalent to what? You see, mass is equivalent to inductance. Clear? Then you here next you see that what is left? That damping coefficient B is equivalent to R. So this is the equivalent analog system. This is clear to you? Okay, fine. Now, then what is the relationship between the displacement? So this displacement, what it is here, x, is equivalent to what? Q. Displacement is equal to the charge which is going to get associated with the circuit. This is okay? Q. So here you see that, or Q is what? Integral I dt. Or you can say another thing is that dx over dt is what? dq over dt? dq over dt, that is I. So dx over dt is what? V. So you can say that speed in your system is equivalent to current, what it is going to flow in the electrical circuit. So now everything is clear. Then another thing is that you see that this is the back EMF and the force. And the force is equivalent to what? Force is equivalent to the back EMF. Clear? So because force is equivalent to back EMF, we say it as force rotation. Now I am not going to draw the second one, force current analogy. Just I give you hint and then please draw by yourself. Okay. But necessarily you have to draw. So when you draw, let's say that we have a mechanical system like this, same arrangement. Okay. Same arrangement is there. This is K, this is M, this is B, and that we want that this should be represented by an equivalent electrical circuit in which the elements are parallel representation of the passive components will be there, like this one. We want that this type of arrangement should be there, and the input this time is current, okay, I. This is R and L C. Done? This is clear to you? That we want this, and this is called what? Force, current, analogy. So now please see here what is common with all. So let's say that a voltage is common with all. You see, this point is same, it is all same, so voltage is common with all. So can we say that this is the input current, and the current here is going to flow is IR, current which is going to flow here is IL, and current which is going to flow here is IC. Remember, in the previous case we have applied Kirchhoff's voltage law. Now what we are going to apply? Kirchhoff's current law. So as per KCL, what we can write? As per Kirchhoff's current law, KCL. Okay, so can we write that incoming current as positive I and outgoing current as negative? This is IR minus IL minus IC. This is equal to 0. So can we write it like this? I is equal to IR plus IL plus IC. And what is IR? E by R. Okay, voltage difference, na? So E by R. So there is E by R. What is IL? You remember that equation was voltage across the this inductor is L di by dt. So what is I? It is integral voltage across the inductor E dt and 1 by L. Okay, this is so here this IL is what? 1 by L integral I integral E dt, na? Integral E dt minus infinity to t. Here also you need to write, because there is a possibility that it will have some initial condition. Then capacitor is IC. We know that IC is equal to what? IC is equal to C d Vc over dt. And what is the voltage across the capacitor? It is back this E. This E is there, which is the voltage across this capacitor. It's all in parallel. Okay, this is our datum node. You can consider that this is a datum node. Okay, so dE by dt. So we can write here C equal to dE by dt. I. Now, very important thing, we have to further solve it. Now, after this, I will give you, you have to do by yourself, and then find out what is the equivalent electrical analogy for this system. Okay, force current analogy. So what we are getting here, you see that one more relation we know. Remember that d phi over dt is equal to E back EMF. Faraday's law. Huh? So can we write that for this E is equal to d phi over dt, the flux. That is Lentz's law. Huh? That is Lentz's law. So when you write your KVL, you remember that I have written KVL, so automatically it will come like this. We are talking about the voltage which is applied across the inductor. It will have the induced EMF because you are applying something, you are trying to inject some current into that, and that is going to oppose that to create a balance. So you see that can we substitute this value wherever, and this is E is there, na? So wherever this is E equal to d phi over dt, and wherever we will see that integral E dt is there, we will represent it by phi. Okay, we will replace it by phi. So substitute here and you will get I is equal to E is what? 1 by R d phi over dt, and this is, you remember what it was? Integral is phi. So it is 1 by L phi plus, this is dE over dt. So dE over dt is what? this is d2 phi over dt square. So can I write here C d2 phi over dt square. So we have again the equations. You please see here. So just because I don't want to switch to the next page, so that's why I am writing again the previous equation of the mechanical system. Ft equal to what? M, oh sorry, I have to rearrange it. Then only it is possible. Just a moment. So I think I need to go to the next page. So next page I am just moving, and then can we write it as C d2 phi over dt square plus what it was? Then 1 by r d phi over dt plus 1 by L phi is equal to I. This is our equation 3 we can write. And then we have the previous equation m d2 x over dt square plus what it was? B dx over dt plus kx is equal to ft. This was our equation 1. So you please see here that when we talk about force current analogy, a mass element can be represented by what? Capacitor. Okay. When then damper will be represented by what? Resistance. 1 by R. Okay. Then spring constant K is written by inductance. So you see everything changes. What do you want? You want series RLC representation or you want parallel RLC? Okay. So for series RLC representation, both they are not in series, so you have to apply linear. And when we talk about both current analogy, because it is parallel, so we have to apply phase series. Okay. So please remember that when you go to industry, you will also listen that electrical spring. So what exactly is that electrical spring? They will say that okay, it is an electrical spring which can store energy spring. Okay. So please remember they talk with respect to this equivalent RLC circuit. So electrical spring is nothing but your capacitor. Equivalent electrical mass is nothing but your inductor. Electrical damper is nothing but a resistor. Okay. So the term of electrical mass, electrical spring and electrical damper. So it is not possible for you to make the analysis with mechanical system, which is very, very complex. So what we have to do? We have to bring whole of your mechanical system, which is under configuration analysis, into small section of this equivalent electrical circuit. You understand? So last class what I explained you, can I go ahead? Yes? Last class what I explained you is that we have the differential equation we have seen. We have to solve the differential equation. So one tool is what? A Laplace transform. So you can do it. Okay. So remember that let us consider that we have a mechanical system or thermal system or any chemical system or anything is there, and you have written the equation of dynamics of that. Okay. And you have compared the equation of dynamics with differential equation with what? That equivalent electrical representation, series or parallel. Done. So now you have electrical system. So you have worked with the electrical system and at times replace the parameters by the mechanical. And the response will be the same okay, as it is going to be for your mechanical system. Imagine. So now what we have to do? We have to analyze that electrical system, what you have made as an analogous one. So what we have to do? So remember that what we have done. We had a mechanical system. We had a mechanical system here, okay, which was like this, okay, this is mass, this is spring, and this is B, okay, and then some force is acting over it, Ft, and because of that, some displacement is going to happen. And so what we have done that we have represented this with an equivalent with an equivalent electrical circuit. So what you will do now to analyze this circuit? You will write again differential equation and then you will solve this differential equation. This is the process what you are going to do. Okay. So this is, let's say, the input E you had given to this. This is R, L and C, and this is the equivalent circuit I. The problem is that we don't want to solve the complex differential equation. Here elements are very simple. It is going to be second order circuit. You say I will solve. What will happen if the more number of elements will come in the system? This is one damper. Maybe other mass elements will come here. 2, 3, 4 mass elements will be there. Then what you will do? It will become very, very complex. Okay. So what we will do, that we will work with this. So you see that this is there. So you remember that last class I explained that if you are having a resistance, then this is I and voltage across this resistor is V. Now this is not speed, remember, this is voltage. I write here it is voltage and this one is current. So you remember that the equation what we have written for this one. So this is equivalent to R in Vs and this is Is in Laplace transform. Clear? Then we have seen, also discussed, that if we are having an inductor, and the current which is going to flow through this inductor, let me write IT, and the inductor is L, and the voltage across this inductor is V, then we have seen that how we represent it. It was represented in Laplace transform domain like this. This is SL and this was Li0. What was the residual flux? Residual flux in that one. This Li is flux, and because of that the EMF will be there. So what is the residual EMF is there in the coil? Because in past we have applied it. And this is Vs, and what the current you are going to allow is Is. Okay. Similarly, if you have a capacitor, then this capacitor is, let's say that the voltage is V and the current which is flowing here is I and the value is C. So this is represented by like this. Okay. So this is 1 by Cs and this one was plus minus Vc0 by S. Remember last class I explained, those who were present, and then the voltage across this one is Vs and the current which is flowing here is Is. Okay, Vs and Is. This is what we are getting. This is clear to you? Now after this, so based on, now another thing, remember that just as a summary I am writing here, when we, let's say that we are having a signal xt, and if you want to make a Laplace transform, it will become xs. If you have the first derivative of the signal xt, you want it, and you want to make the Laplace transform, this will become s xs minus x0 plus, okay, x0 you write, x0 minus we right here, and if we have integration of this xt dt and we want to obtain the Laplace transform of this one, then it is going to be 1 by s xs plus x0, not x0 rather, it will be integral of basic of this one. Let's say that this is y. Okay, so it will be what? y0, not x0. It will be integral, the initial value of that one. So let me write here, erase it. So this is going to be y0 by s, means the initial value of this integration, minus infinity to t. Okay, so let me put a mark. This is Okay. Huh? Clear? So this is we discussed it. So now you are having what? A circuit like this. A circuit like this. So what we can do now is that this circuit, that this is in time domain. So equivalent circuit in Laplace transform domain will be written by what? You draw the same circuit. Here we are assuming that the circuit is initially relaxed. Means at the beginning it is relaxed. Clear? So this is what? So this E will become what? ES. This R will become R. This S will become SL, and this capacitor will become 1 by SC. Why? Because we are assuming relaxed, so this portion is 0, this portion is 0. Okay? And the circuit current will be what? Simply IS. So this is the equivalent representation of the system. So, like in some cases when you ask about the transfer function. So you can write down again the KVL here, again the KVL. You can write down again the KVL. So it is what? It is rising potential. We are moving in the direction of current, so it is minus ISR. Then it is minus minus IS SL. Okay, and then it is minus 1 by SC IS, that is equal to 0. So when you represent, rearrange it, you will get ES is equal to IS R plus SL plus 1 by SC. Okay, so what you can further rearrange it, and this IS by ES, okay, is equal to what? 1 by R plus SL plus 1 by SC. So this is what you are observing is called transfer function. Okay. This is the transfer function. Transfer function. Transfer function of this system in which output is IS and input is ES. If you want that, no, I want to know that what is how the voltage across this resistor is going to change. Voltage across this resistance is going to change. So this resistance is equivalent to your damper, and current is equivalent to what? Speed. So voltage will be equal to what? You can make all the relationships. Okay, V equal to L derivative. So you can relate with this acceleration will become. So all the things make the relations you can do. So you can analyze, think for the damper, you can think for here and correlate with your damper. So this is what it is there. But and then you can further solve it. You can, if you want, you can further solve it. So let me solve it just. So it is going to be S by L. So it is S square plus R by LS plus 1 by LC. Okay, this is what you are seeing, the transfer function is there. But the problem is that when you are going to, this is your second order differential equation. You will make a partial fraction, inverse Laplace, all these things you will become very complex. You will not be able to solve, okay, for a complex system. This is a simple system. So what we do that we go for element wise representation. This we will make each of the system into small elements. In MATLAB, you have the electrical circuit, PCM and so many tools are there in MATLAB. You can run it, see the response back. For the complex problem will be more. Okay. So what we do that we can represent this circuit as an equivalent representation or block diagram representation. Please remember that just I want to show you that what we have done. Let me copy it. Okay, this one is there. So I'm just copying. Oh, sorry. This part of copying. Whatever will come. Let me see here. This is there, no? This is what we have seen. Vs. Okay. So this block, suppose that a resistance is there. So let us consider that if you give an input as current here and the gain is R, then it will be giving an output V. Okay. If you want to write it in Laplace transform domain, if the current is Is, this is R, it will become Vs. Okay, Vs equal to Is into Rs. Suppose that to this element, if you apply some voltage, let's say Vs, then what is the current? This is going to be the current. This is clear? Okay. Similarly, this inductor is there. Okay. So in inductor, if you give, let's say a current here, you apply a current here, Is. So we are representing in terms of block. Okay. And this is SL. This is impedance basically. So Is into SL will be what? It will be voltage across this inductor. Similarly, let's say that you give input to this, you know the input across this inductor. So what is the current which is going to flow through this one? This will be the current. Please cross check. Cross me like if it is not clear to you. Similarly, if you have a capacitor, this capacitor, and if you are giving a current into this one, okay, if you are giving, let me write in Laplace transform domain, otherwise you will have to take the help of integral or differentiation. Okay, Is is there, you are giving here, so so Is is there, and impedance is 1 by SC, so output will be what? It is the voltage across this capacitor. Okay, and if you give, let's say, voltage into this capacitor, apply some voltage across this capacitor, so how much will be the current? Is will be SC. Clear? So this is what we are doing now, that we are representing our elements, each of the element by a small block diagram representation in Laplace transform domain circuit, okay, which will be there in the MATLAB or Scilab. Clear? In some cases, when you will work with Scilab or MATLAB, you will not find this S. Okay? You will not find S. S is differentiation. It will not be able to do it. So you will have to do what? That this input will be given V S, then you will multiply, put a gain C, and then here you will see that in the MATLAB or that du over dt is there. So you will have to use that du over dt. Just to represent S. Okay? This S, this is S. Huh? And then you will be able to get it. Differential S will be. Why? Because there is a concept of proper and improper function. You remember? Proper function is one in which degree of numerator is less than or equal to degree of denominator. Improper function is what? In which degree of numerator is more than the degree of denominator. So all these systems, transfer function approach and all these things are valid for proper system. Clear? Proper system. So that's why you will have to use du over dt. Okay, just I will take 5 more minutes so that we complete it. And then I request you that please think for how you are going to represent that RLC by element wise representation. So let me consider one circuit. Let's say that we are having R. Let's say here a capacitor is there, C, and here an inductor is there, L, and it is feeding a load. It could be representing any of the mechanical system. Okay, so this is R. क्या हुआ कहाँ जा रहे हैं? Okay, you will reach there 10 minutes later. Sit down. Okay, sit down. I think I can take some time. This is L and C, and this is the output what you are willing to observe, VO. Okay, and this is the input what you are giving here, E. Okay, so please remember what we have to do, that we can consider here that to each mesh you assign current. So let's say that this current is I1, very first step. Second is I2, okay? And then to each node you apply some voltage V. Let's say this is V and this one is VO. This is your data node. You have to identify it. Then obtain the equivalent Laplace transform circuit. You see that how fast I do. Okay, so this is R, sorry, R, this is R1, you can write R2, this is R2, this is R1, and this one will become what? SL. This will become what? 1 by SC, and the output will become BOS. Input will become what? ES. The current which is going to flow in the circuit is I1S. This is what? I2S. Okay, and this voltage will become Vs. Now let's start making block diagram representation. So when you find a series element, you have to find current. When you find a parallel element, you have to find voltage across it. So first element is series element. What we have to do? We have to find current through this. So what is the current? Voltage across this is ES and Vs. So across this resistance is ES minus Vs. So this will be represented by, this is, you see that, ES plus minus Vs. So this becomes what? ES minus Vs divided by the resistance R1. So what we will get? Current. Which current? The current which is flowing through this one. This is I1. So this is I1. Okay. Then next is what? We have parallel elements. So we have to find voltage. Okay. So you see that to this capacitor, one current is flowing in this direction and another current is flowing in this direction. So it is I1 minus I2. You have to reference first one. I1 minus I2. So this I1 is there. Then this is plus and this is minus. So I1 minus I2 means it is I1S minus I2. Okay, so this will be multiplied with what? In the capacitor is there. So I multiplied by impedance. So that is, impedance is 1 by SC. Done? Okay, so what it is? This is the voltage across this capacitor. Vs. Now series element is coming. So what is the voltage? Vs and Vo. So you have to write Vs minus Vos multiplied by what? This is voltage divided by impedance. So divided by SL. So what you are going to get? The current which is flowing through this is I2. So here it will be I2S. What is the final element? R2. So I2 multiplied by the resistance is R2 is going to be VOS output. Now please connect all. So you see that VO is here. Where is I2? This is here. Okay. Then where is V? This is here. Okay. So now what you see is called element-wise block diagram representation of stacked electrical circuit, which could be represented or is analogous in mechanical system, in thermal system, in chemical system, whatever it is. So now you will be putting these blocks in Scilab or MATLAB. You give any input to ET, maybe step input, sinusoidal input, ramp input, whatever you want to do, and accordingly you can observe the voltage, current, this point voltage across the capacitor, each and every variable you can understand. But if you would have done with this only transfer function approach, it could have been very, very complex for you to analyze. Okay, so that's why we use some simulation software to simulate these block diagram representations. See that. So if you study control system or something, you see these blocks only, which is G1, G2, G3 like they write, or H1, H2, H3, and you use block diagram reduction methods. Okay, transfer reduction method to solve the obtain the overall transfer. Okay, so this please simulate in MATLAB. Now you know the basic. Consider any value of R, L, and C and simulate in MATLAB. And then I request you that please obtain the equivalent analogous system for this one also. Think how you are going to do it. Element wise, I want element wise. Put your mind. You can consider the voltage across each of the element. Okay. So please, sorry that I have taken a little bit more time, but you also. Okay, in any case, So I will save this one with you.